Thank you for the introduction. I'm Euan from University of Glasgow, and today I'm presenting our paper on PointandShake, which is a new interaction technique for selecting objects in a levitating object display. As the name suggests, a levitating object display is the type of display where the content is composed of several objects levitating in midair. Unlike traditional screens, which are made from joined up pixels, a levitating object display has lots of distinct objects that levitate instead. I'm not having a lot of luck with this laptop today. I think I've crashed PowerPoint again. Let's see. Nope, sorry, I'm going to have to skip that. Basically, the video was showing another example of acoustic levitation, which is what this work focuses on. So we're using sound to levitate small particles in midair in a controlled fashion. And by manipulating the acoustic field inside that device, we can position and move the objects, just like we can manipulate content shown on a screen. So levitating object displays are interesting for a few reasons. As a novel type of display, they have many unique properties, and that can lead to new ways of interacting with information. So the display primitives in this type of display exist within an invisible volume. You can see through the display and the content it shows. So this means you can see the display from several angles, and if you have groups of users, then they can see the content and each other as they interact with it. These displays could also be combined with other types of display or media. So for example, you could have levitation in front of a normal screen or in front of paper to add an extra controlled level of depth for that display. Users can also reach inside the display volume and can perform other interactions within that space. So new interaction techniques and applications could be built where users manipulate physical objects inside the display. So they use the space between and around the pixels in some meaningful way. The use of sound for levitation means that these devices could also provide non-visual output as well. So the same or very similar techniques to what we're using are also used for parametric audio and mid-air haptic feedback. So future versions of these devices could create haptic and audio feedback that comes directly from inside the display as well. So interfaces based on, sorry, I'm going to restart PowerPoint. Interfaces based on object levitation have mostly only been studied from a technical perspective. So looking at ways of controlling and manipulating levitation. So there hasn't really been any work into interaction with this type of display yet. So we started by focusing on object selection. Selection is a fundamental interaction technique that precedes many other actions. So before users can query, control, or manipulate something shown on a display, they first need to select it. So the aim of this work was to design and evaluate a technique for selecting levitating objects. Designing interaction techniques for levitation is not straightforward. To illustrate this, I'll use one of our devices as an example. So the image on the slide there shows an acoustic levitation setup. On the top and bottom, there are two arrays of ultrasound transducers, and those face each other. The red card at the back there is just to increase visibility, but you could otherwise look straight through it. So inside this display, there are two small polystyrene beads, about 2 millimeters in size, and they're being held in midair by standing sound waves created by the ultrasound arrays. By manipulating the acoustic field produced by this device, those objects can be independently moved within that space. Otherwise, the levitation is very stable, and the sound field is also inaudible because the ultrasound is out with our hearing range. So one of the main interaction challenges here is that users can't always directly manipulate the objects inside the display. This is partly due to their small size and the small distance between some of the objects, like on the previous slides. But a problem specific to acoustic levitation is that the ultrasound frequency we're using is almost entirely reflected by the skin. So reaching inside the display is possible, but as your hand approaches it, you may cause some of the objects to fall, even if you don't directly touch those. Another interaction challenge is the limited amount of information that you can actually convey using this type of display. So the only visible elements are the objects themselves, so any feedback about interaction needs to be given through the appearance and behaviour of those. With those constraints in mind, we designed a selection technique that we called PointandShake. This is a selection technique that uses mid-air pointing gestures for input, and all feedback required during the interaction is provided through object movement, so we manipulate the appearance of the levitation to support the user. The name comes from the combination of the pointing input gestures and the shaking feedback, and I'll now demonstrate that. So as you can see in the video, the user starts pointing at objects to target them, and the targeted object shakes from side to side as feedback. I'll just play that one more time. So as the user brings their hand up to the device, they start pointing at the object on the left. We manipulate the acoustic field in the device in order to shake the object on the left, as you can see there. The user starts to point at one on the right and then back to the left again. So I'll now talk separately about the point and shake parts of the interaction, starting with point. So as you saw in the video, users can target objects by pointing at them. This is implemented using Recastpointing. So when the user extends their finger towards the device, an imaginary ray extends in the same direction as their finger, and any intersected object is targeted. After 1 second of targeting, we consider the object to be selected. We use this dwell period to avoid unintentional selection when pointing near other objects. Because of the small size of the objects that we're levitating, we use virtual targets to increase the effective target size. So basically place a sphere around each object. If the ray from the finger intersects that, then that's the one the user's targeting. The image on the right there shows an example of a larger target volume placed around the bead. Because we're using acoustic levitation, the objects need to be separated anyway, so this doesn't really have too much of an impact on the display resolution. We can't put them immediately close to each other, otherwise the acoustic traps would combine. So to create the shake feedback, we rapidly move the levitating object in small steps to the left and right of its original position. The image on the slide there shows the steps that we use to create the appearance of the object shaking. This feedback was simple, but it conveyed everything that the users would need to know during interaction. So if they point at an object and it shakes, then they're targeting it successfully. The absence of any feedback suggests that the system isn't interpreting their input in the way that they'd intended to. So we did 2 studies into this technique. The first evaluated point and shake with a range of different target sizes. As I mentioned a couple of minutes ago, virtual targets basically increased the effective target size in order to improve usability. So the aim of this study was to see if users could successfully interact when the only feedback given was by the object shaking. Pointing gestures have been used with other types of display before, but in those cases the displays were used to show things like cursors or pointer trajectories. In our case, the amount of feedback available was constrained, so we wanted to see if this was enough to enable usable interaction. The hardware set up for this study was the same as I showed earlier on. There were 2 objects, and the experimental task was to select either the left or the right one. We varied the size of the target surrounding each object from 5 up to 30 millimeters. So we varied the target size to see how this affected usability, so that we could use the results to try and balance usability with display resolution. Ideally, we'd have had a higher number of distracted objects, but at that time 2 was the most that we could levitate and independently move without affecting others. Since this work's been completed, advances in acoustic field synthesis have overcome this, and we can now independently levitate and shake more objects. So overall, the point and shake interaction was successful. Users completed 96% of tasks within a given time limit. Almost all of the failed tasks were for the 5mm target size, and those ones failed because the user ran out of time for that task rather than because they selected the wrong object. Average selection time was 4 seconds, although as you can see in the chart there, that was significantly higher for the 5mm target size. As target size increased, the selection time decreased, as you might have expected. The time here includes at least 1 second dwelling on the objects to confirm the selection as well. So to summarise the results of that, the selection was difficult with 5mm targets, and that's reflected by both success rate and selection times. Interaction became easier as target size increased, which wasn't really surprising, but based on our results, we recommend using 10mm target sizes. That offers a good trade-off between the display resolution and the usability of interacting with these devices. The wavelength of sound used for levitation means that objects need to be separated by 5 millimeters anyway, so this minimum separation is only double that, so we still have quite a reasonable resolution from this. So the primary goal of this study was to see if point and shake was usable in its simplest case, and the results suggest that it was. So in that first study, we focused on the simplest case of interaction, where users were able to point directly at the object they wanted to select. In practice, object occlusion might be a problem. So this is when the selection target is hidden behind other objects in the display. So the images on the slide here show an example of that. Pointing at the furthest away object is difficult because the user first has to point at the one that's in front of it. This is a limitation of Recastpointing, but techniques have been developed to allow users to select occluded objects. So we adapted point and shake to support the lock ray technique, which was originally created for volumetric displays. Lock ray is a version of Recastpointing that allows users to select occluded objects. So here, selection takes place in 2 steps. First, the user aims the ray, potentially targeting multiple objects. Then the next step is to move a cursor back and forth along the ray in order to select the hidden object. So the images on the slide there show an example of how the fingertip position allows the user to select one of these 2 intersected objects. So by moving the finger forward, the user can target the furthest away object. By pulling it back, they can get the one that's closest to them. There are alternatives to lock ray for dealing with occlusion, but this is a simple technique because it breaks the interaction down into 2 steps. So that makes it ideal for levitating object displays where the amount of available feedback is constrained. This is probably best demonstrated with a video. So what you'll see here is the user starts pointing at the 2 objects and they both shake from side to side to show that they're being targeted. The user then extends their thumb to lock the ray in place. At this point, the fingertip position relative to the device determines which object is targeted. So here, the user is targeting the object closest to them. As they move their finger forward, they're selecting the one in the back. So we looked at 2 methods for confirming these selections. One we called quick release, which was simply closing the thumb, ending that gesture, and then the final object is selected. The alternative was to use dwell, as we did before. So the user basically selects the object for 1 second, and then it's finished. So this brings us to our second study, where the aim was to see if users could use this more advanced technique effectively. The fundamental interaction was the same, but the extra steps added complexity, and we were interested to see if the shake feedback could still support successful input. The setup for this experiment was similar to the first one, except we asked the user to select the object either closest to them or furthest away. And the requirement for that task was that they first had to aim the ray towards both objects to force them to actually use the disambiguation step. Otherwise, they could have just moved their hand to the side and directly pointed at the object. In this study, we also compared quick release and dwell, which were the 2 techniques I mentioned a second ago. So the results suggest that our version of lock ray was successful. Selection accuracy was just over 94%, and the selection time was 3 seconds on average, and that includes the 1 second for the dwell in that case. The selection time was faster than in the first study, although in that case the average time was slightly higher because of the most difficult condition. The charts on the slide there show the total selection time, and then that's broken down into 2 steps. First was the amount of time spent aiming the ray, and second was the amount of time spent disambiguating between the 2 targets. So total time was significantly faster for quick release, and that was because it had faster disambiguation time. That wasn't entirely surprising because quick release lets users confirm selection without having to wait for a dwell period to elapse. Although this result's interesting because it shows that users generally did decide to confirm selection straight away. Because of the complexity of the task and the constrained amount of feedback we could give, we weren't sure if users would actually feel confident enough to do this. But the results suggest that they did, and most of them also preferred quick release for that reason. So to summarise what I've just spoken about, levitating object displays are a new type of display where content is composed of several small objects, levitating in midair. Interaction with these displays hasn't been studied properly yet, so this was the first study of interaction with levitating objects. We started with selection because that's a fundamental interaction that's necessary for other more complex actions to take place. We designed a selection technique that we called point and shake, which combined mid-air pointing gestures with object shaking as feedback. We evaluated that in 2 studies and both found that the technique was relatively successful. These results are interesting because they show that our method of giving feedback was a success, and that paves the way to more complex interactions with levitation. Finally, just before I finish talking, a teaser for CHI 2019, which we're bringing to the best place in the world next year. So please come along to the keynote this afternoon and find out more about that. Thank you for being a great audience. I'm happy to take any questions.
Okay, so I have a question while the attendees get ready with theirs. The shaking mechanism, how do you think it will translate when you scale the objects up, or for example, when there are a lot of objects that are really close by and grouped together, how do you think that'll work?
Yeah, that's a super important question. We did cover this a bit more in the paper. So we're using sound waves to levitate these objects. In order to move the objects in midair, we have to basically move the sound wave from side to side. That's going to have an effect on the levitation because if they get too close to each other, 2 objects would basically be sucked into the same trap. So we did some work into trying to find what the minimum separation was for the objects to still allow us to, move them from side to side without affecting each other. That was fairly minimal, so I think the paper reports the exact number, but it was something like 0.3 millimeters was the extra distance we needed to actually create that visible feedback. So when you think about the 10 millimeter separation that we need for usable interactions and the 5 millimeters that we need in order to actually allow several objects to be levitated, that extra 0.3 is like a very small proportion. So as we get better acoustic algorithms as well, we could also compensate for that kind of thing. So yeah, it's an important factor, but it's a small part of the sort of display constraints there.
Great, thanks.
Cheers.
Hi, Euan. Do you think these can be extended to multiple particle selection? So just like you can bunch them together or something like this?
Yeah, so what we did in this, but I never mentioned in the presentation, was that we used this to allow sequential selection. So you could point at one object, then another, then another. What we did to disambiguate between objects that were already selected and ones that weren't selected was basically shake them from side to side, but at a much slower rate, so that was still visibly distinct. I think it'd be kind of interesting to look at more complex techniques where you select them in one step rather than in sequence. So I don't know, maybe drawing around multiple targets or something like that. So there was a cool paper the other day about multi-finger raycast pointing, which seems like a kind of a good direction for this to go in with regards to that.
Thank you.
Thank you.
All right, let's thank our speaker.
Thank you very much. Come to Glasgow next year.